A place exists in space so empty that if our entire galaxy sat inside it, you would see nothing. No stars, no light, just silence in every direction. Somewhere else, iron is falling from the sky right now. A black hole sits at the center of a galaxy wide enough to swallow our entire solar system without even slowing down. Tonight, we visit the places in this universe that should not be real. A void that breaks cosmology. A structure too large to have ever formed. And something pulling millions of galaxies toward a point no one can see. If this kind of exploration does something to you, hit like and subscribe. We are just getting started. Prepare yourself. We begin. Imagine pointing a telescope at a random patch of sky and finding absolutely nothing. Not a dim star, not a distant smear of light from a galaxy billions of light years away. Nothing. Just darkness stretching further than the human mind was built to process. That is the Bootes void. And astronomers have confirmed it is real. Located roughly 700 million light-years from Earth, the Bootes void is a spherical region of space approximately 330 million light-years across. To understand that scale, consider this. The entire Milky Way is only 100,000 light-years wide. The Bootes void could swallow 3,000 galaxies like ours, lined up end to end, and still have room left over. Here is where it gets strange. When cosmologists model how the universe forms over billions of years, matter should clump together along what scientists call the cosmic web. Gravity pulls gas into filaments. Filaments collapse into galaxies. Galaxies gather into clusters. Empty regions form, yes, but they are modest. They are expected. The Bootes void is neither. By every known model of cosmic structure formation, a void this large should not exist. It would take around 100 billion years for such an emptiness to grow naturally through gravity alone. Our universe is only about 13.8 billion years old. The math does not work. This is a confirmed measurement, and it remains one of the most unsettling open questions in modern cosmology. So what happened here? One theory, still debated, suggests the Bootes void formed when several smaller voids merged over time, creating one vast emptiness far larger than any single region should produce. That explanation is considered plausible by some researchers, though it still does not fully account for the size. Another idea, discussed less officially but not dismissed, is that the void is so anomalous it hints at physics we do not yet understand. Forces acting across vast scales, structures beneath the structure of the universe itself. And here is a detail that sits quietly at the edge of this mystery. In 1981, astronomer Robert Kirshner and his team stumbled upon this void almost by accident while mapping galaxy positions. They expected to find galaxies. Instead, they found a hole in the universe. When they published their discovery, the response from the scientific community was largely disbelief. The void was so large that several researchers assumed the data must be wrong. It was not wrong. Inside the Bootes void, astronomers have since identified a small number of galaxies, roughly 60 confirmed. But in a region that size, you would statistically expect to find around 2,000. What happened to the other 1,940? Where did the matter go? That question does not have a clean answer yet. If you stood on a world inside the Bootes void, you would look up at a sky with almost no visible galaxies, no neighboring lights, no cosmic company in any direction. You would be alone in a way that no life on Earth has ever experienced or imagined. The void stares back. And the universe, it turns out, has gaps in it that make our entire existence feel like a tiny island in a sea with no shore. But emptiness as terrifying as it is, may be less frightening than what is actively pulling us forward. Something is pulling us right now. As you listen, our galaxy, along with millions of others, is moving toward a single point in space at around 1,400,000 miles per hour. We are being drawn. Scientists call it the Great Attractor, and for decades they could not even see it. The Great Attractor sits in the direction of the Centaurus and Norma constellations, roughly 250 million light-years away. It represents a gravitational anomaly of staggering scale, a region where the combined mass of tens of thousands of galaxies, dark matter, hot gas, and unknown structures creates a pull so powerful it bends the paths of entire galaxy clusters across hundreds of millions of light-years. This is confirmed. The movement is real and has been measured with precision. The problem for most of the 20th century was that the Great Attractor sits almost perfectly behind the plane of our own galaxy. Dust, gas, and the dense star fields of the Milky Way blocked our view almost completely. Astronomers knew something massive was there because they could feel its gravitational effects, but they could not look directly at it. It was like knowing a fire exists because you can feel the heat through a wall, but never being able to see the flame. In the 1980s, researchers mapped the velocities of thousands of galaxies and found they were all converging on the same region. The name Great Attractor was coined because no more precise description existed. Something great was attracting everything. When telescopes finally pierced through the galactic plane using longer wavelengths of light, what they found was the Norma cluster, a dense supercluster of galaxies at the core of the attraction zone. Massive, ancient, confirmed. But it still was not enough to explain the full force being measured. And then things got more complicated. Further behind the Great Attractor, scientists identified something even larger. The Shapley supercluster, a colossal structure 500 million light-years away, containing hundreds of galaxy clusters and enough mass to exert gravitational influence across an almost unimaginable distance. Some researchers now believe the Shapley supercluster contributes significantly to the movement we feel. Others argue there may be still more pulling from even deeper in that direction. Here is what that means for us personally. We are not stationary passengers in the universe. Every second, our position in space shifts, not just because the universe expands, but because something enormous is tugging us. Our galaxy, the Andromeda Galaxy, and the entire local group are all being swept along toward a destination we will never reach in any human timeframe. The unsettling part, confirmed by modern measurements, is that even as we are pulled toward the Great Attractor, the expansion of the universe is simultaneously working against that pull. Eventually, the acceleration of expansion will win. The galaxies being pulled together today will, billions of years from now, be scattered so far apart that no gravitational force will hold them. For now, though, something is calling. Millions of galaxies answering without a choice. Gravity is invisible. It crosses every distance. And what lies at the origin of that pull is still officially classified as not fully understood. But while the Great Attractor drags entire galaxies without effort, somewhere in the universe, a single spinning object is doing something that should be physically impossible. A dead star is spinning over 500 times every single second, not rotating gently like a planet, spinning at a speed where its surface is moving at a significant fraction of the speed of light. And it has been doing this without slowing down for possibly billions of years. This object carries the designation PSRJ0952-0607. But for this journey, we will call it the Black Widow Pulsar. It earned that name because of how it feeds. A pulsar is what remains after a massive star exhausts its fuel and collapses in a catastrophic explosion. The core that survives is compressed beyond imagination. A sphere roughly 12 to 15 miles across, containing more mass than our entire Sun, packed so tightly that a single teaspoon of its material would weigh around 10 billion tons on Earth. That is confirmed science, verified through decades of observation. Normal pulsars slow down over time. They spin fast at birth, then gradually lose energy, like a top that winds down. The physics are clear and predictable. So when astronomers first observed pulsars spinning hundreds of times per second, they had to reconsider what was happening. The Black Widow pulsar is what scientists call a millisecond pulsar. It was spun back up to extreme speed by stealing material from a companion star, a process called accretion. As gas and matter fell onto the pulsar, it transferred angular momentum, pushing the dead star faster and faster over millions of years. The pulsar consumed most of its companion in the process. What remains of that companion is now a faint, burned-out remnant being slowly devoured, hence the name. But the speed alone is not the most unsettling part. In 2022, a research team measured the mass of this pulsar and found it to be approximately 2.35 times the mass of our Sun. That placed it at or beyond what many physicists considered the maximum possible mass for a neutron star. The theoretical upper limit before gravity should win completely and collapse the object into a black hole. This pulsar should not exist. According to several models, it should have already crossed that threshold and vanished. Instead, it spins on. One possibility is that our models of the maximum neutron star mass are wrong. Another is that this object contains exotic matter deep inside its core. A type of quark matter that behaves differently under extreme pressure. That idea is currently theoretical but actively studied. The implications are significant. If a neutron star can exceed predicted mass limits and survive, the boundary between neutron stars and black holes is less defined than science assumed. Objects may exist in that gap, strange hybrid remnants, neither fully one thing nor the other. There may be categories of objects in this universe that our current physics cannot properly name. For now, the Black Widow pulsar spins, steady, relentless. 500 rotations every second, over 1 billion rotations every day. Broadcasting its presence across the galaxy in pulses of radiation precise enough to rival atomic clocks. And deep in the fabric of space, something even colder and stranger is waiting for an explanation that science has not yet found. A patch of the sky is wrong. Not dangerous, not moving, not emitting anything unusual. Just wrong in a way that has quietly unsettled cosmologists since it was first confirmed in the early 2000s. The cold spot is a region of the cosmic microwave background, the faint glow of radiation left over from the earliest moments of the universe, roughly 380,000 years after the Big Bang. This background radiation fills the entire sky and is extraordinarily uniform. Temperature variations across it are tiny, measured in 100,000ths of a degree. But the cold spot is different. It is significantly colder than everything around it. And it is enormous. This region spans roughly 1.8 billion light-years across. The temperature difference is small in absolute terms, but in the context of the cosmic microwave background, where such uniformity is expected and demanded by theory, it is a glaring anomaly. Confirmed. Measured by multiple independent space missions, including the Wilkinson Microwave Anisotropy Probe and the Planck satellite. Standard cosmological models predict that temperature fluctuations in the background radiation should be random and distributed roughly evenly. A cold spot this large, in a single location, has a probability of occurring by chance of less than 2%. That is uncomfortable for a model supposed to describe the entire universe. So what is it? The leading physical explanation is that the cold spot is caused by a supervoid, a vast region of space with significantly less matter than average. As light travels through a supervoid, it loses a small amount of energy through a process called the integrated Sachs-Wolf effect. Less matter means a shallower gravitational well, and light traveling through it arrives slightly cooler. In 2015, astronomers found evidence of a supervoid in that region, roughly 1.8 billion light-years across, and located around 3 billion light-years from Earth. If confirmed fully, it would be the largest known void ever identified, larger even than the Bootes void. But here is where it gets more interesting. The supervoid alone may not fully explain the temperature difference. The numbers are close, but some researchers argue the supervoid accounts for only part of the anomaly. The rest remains unexplained, and that leftover fraction has opened the door to stranger ideas. One hypothesis, theoretical and actively debated in quantum cosmology, suggests the cold spot could be a remnant of a collision between our universe and a neighboring universe. An imprint left from before the Big Bang, when two separate regions of space-time made contact. If true, this would be the first observational evidence that other universes exist. This idea is not confirmed. It is not even the mainstream view, but it has not been ruled out. In cosmology, a region that is slightly too cold in a slightly wrong place has led some of the most careful thinkers in physics to seriously consider rewriting the rules of everything. The cold spot is a data point so stubborn it has forced an entire field to ask whether our universe is one of many. And while the cold spot is cold in the most abstract cosmic sense, the next stop introduces something that makes cold completely irrelevant. A force so extreme it would kill you from a distance that should feel completely safe. The most powerful magnetic field ever measured in the universe didn't come from a black hole or a galaxy. It came from something the size of a city. Magnetars are a rare class of neutron star. They share the same extreme density as pulsars, a city-sized sphere of impossibly compressed matter. But what sets magnetars apart is their magnetic field. Roughly 1,000 times stronger than that of a standard neutron star, and roughly 1 quadrillion times stronger than Earth's. To understand what that means physically, consider this. Earth's magnetic field is strong enough to deflect compass needles and shield us from solar radiation. A magnetar's field is so intense that from a distance of 1,000 kilometers, it would distort the electron clouds around every atom in your body. The atoms themselves would stretch and deform. Every molecule in you would be restructured. You would not survive. Confirmed by physics, not speculation. The strongest magnetar ever measured carries the designation SGR 1806-20. In December of 2004, it released a burst of gamma radiation and X-rays so powerful that even though it was 50,000 light-years away on the far side of the galaxy, the energy pulse ionized Earth's upper atmosphere. Instruments around the world detected the event. Satellites temporarily saturated their sensors. From 50,000 light-years away, a single flash from this object affected our planet. Magnetars form through the same core collapse process as regular neutron stars. But the exact conditions that create such extreme magnetic fields are still being studied. One leading model suggests they form when the rapidly spinning core of a collapsing star generates a dynamo effect, amplifying the magnetic field to extraordinary levels in the first seconds of the stellar death. But here is where magnetars become even more unsettling. They are unstable. The crust of a magnetar is real and solid, and it is under constant stress from the magnetic field twisting and straining the material beneath it. Periodically, the crust cracks. These events are called starquakes, and they release enormous amounts of energy in milliseconds. The gamma-ray burst from SGR 1806-20 in 2004 was triggered by exactly one of these crust fractures. A starquake on Earth releasing the same proportion of energy relative to our planet's mass would be enough to destroy it entirely. On a magnetar, it registers as a moderately large event. There are currently roughly 30 confirmed magnetars known to science. Given the size of the galaxy, there are likely many more that have not been detected or have already faded. Magnetars lose their extreme magnetic energy over roughly 10,000 years, slowly becoming more conventional neutron stars as the field decays. For that 10,000-year window, they are arguably the most energetically violent objects in the known universe. An object the size of a city producing more energy in a fraction of a second than our Sun emits in hundreds of thousands of years. Now imagine a star that does not explode, does not spin wildly, and does not erupt. Imagine instead a star that simply sits there, cooling, hardening, becoming something that physics says should not be possible at those temperatures. A star should be a ball of plasma. Hot, turbulent, gaseous. That is fundamental. Plasma is what stars are made of. That has been confirmed through every observation in the history of astronomy. The neutron star catalogued as RXJ 1856.5-3754 does not behave that way. Located roughly 400 light-years from Earth and discovered in the 1990s, this object quickly became one of the most puzzling entries in the modern astronomical catalogue. What scientists found when they studied it closely challenged basic assumptions about what a stellar remnant can be. The surface of this object appears to behave like a solid. Not solid in the way a rocky planet is solid, but solid in a far more extreme sense. Data collected through X-ray observations suggests the surface may be in a state called crystalline neutron matter, or possibly something resembling a solid quark star surface, densely packed and rigid in a way that plasma simply is not. This interpretation is not fully confirmed. It is the leading reading of the observational data, and it is actively debated. But the measurements that prompted it are real. Here is why it matters. When scientists calculated the radius of this object based on its temperature and luminosity, the number they got was smaller than any model of a neutron star predicted it should be. A normal neutron star of this mass should be larger. The object appeared more compact than theory allowed for ordinary neutron matter. One explanation is that the interior is made of strange quark matter, a hypothetical but theoretically valid form of matter in which quarks, the particles that make up protons and neutrons, are no longer bound inside individual particles, but exist in a free, exotic state. A star made of this material would be denser than a neutron star, smaller for a given mass, and potentially more stable over time. If that is true, this object is not technically a neutron star at all. It would be something called a quark star, a category of object that has never been definitively confirmed to exist. The surface temperature of this object sits around 400,000 degrees Celsius. That heat is left over from the catastrophic stellar explosion that created it. It is slowly cooling. The light it emits is almost perfectly thermal, meaning it radiates in a way that matches a smooth, single temperature surface rather than the turbulent emission you expect from plasma. This alone is strange. Neutron stars are usually active, variable, complex objects. This one is almost eerily quiet. It does not pulse, it does not burst. It simply radiates steadily, like a glowing crystal cooling in the dark of space. One of the most compact and dense things in the universe. Possibly made of matter no laboratory on Earth has ever produced or observed. For 400 light years, it has sat there, silent and dense, neither fully understood nor easily categorized. Something positioned between what we know and what we have not yet discovered. If the idea of a solid star is difficult to process, hold that feeling, because the next object requires no imagination at all. It simply requires you to accept that something exists which could swallow everything our solar system has ever contained without slowing down. There is a black hole so large that describing its size in miles produces a number that loses all meaning before you finish hearing it. TON 618 is an ultra-massive black hole located approximately 10.4 billion light-years away. It was identified through the extraordinarily bright quasar it powers, one of the most luminous objects ever detected in the observable universe. The light we see from it today left before Earth even existed. Its mass, 66 billion times the mass of our Sun. Confirmed through spectroscopic measurements of gas orbiting it at high velocity. To put that in any kind of frame, the average supermassive black hole at the center of a galaxy has a mass of a few million to a few billion solar masses. TON 618 exceeds even the largest of those by a significant margin. It sits at the outer edge of what physics currently allows for black hole mass through known growth mechanisms. And several researchers have raised the question of whether standard models of black hole formation can account for something this enormous forming in the time available since the Big Bang. The event horizon of TON 618, the point of no return beyond which nothing escapes, has a diameter of roughly 60 billion miles. Our entire solar system, from its central star to the outermost known edge, spans roughly 9 billion miles. TON 618's event horizon is about 18 times wider than that. Every planet, every moon, every comet and asteroid in our solar system would fit inside it with vast room to spare, and it would not notice. The gravity at the event horizon of a black hole this massive is, paradoxically, not extreme by human standards. You could cross the threshold without feeling anything immediately unusual. No wall, no visible boundary, just space. And then the slow realization, as your instruments confirmed your calculations, that all paths forward led inward and none led back. That is one of the most disorienting facts in all of physics. The larger a black hole, the more gentle the transition across its edge. The trap is elegant, almost invisible. Inside, as best as current theory describes, information is compressed. Space-time curves toward a singularity, and the rules of physics as we understand them break down. What actually happens inside a black hole remains unknown. The mathematics produces answers, but those answers require a framework we do not yet have. TON 618 is so massive that its sphere of gravitational influence extends hundreds of thousands of light-years into surrounding space. Every galaxy within a certain radius is, in some small way, feeling its presence across 10 billion light-years of cosmic history. It powered a quasar bright enough to be observed across most of the observable universe. It consumed enough material to build a mass 66 billion times that of a star. And it did all of this so early in the universe's history that astronomers are still working out how it grew so large, so fast. The next time someone describes space as mostly empty, remember TON 618. Space does not simply contain things. It contains objects whose scale defies every intuitive framework humans have ever built. And if a single object can do this, imagine what a structure spanning hundreds of millions of light-years looks like. The universe has a skeleton. Zoom out far enough past individual galaxies, clusters, and superclusters, and what you find is a vast web of matter. Long, thread-like filaments stretching across hundreds of millions of light-years, connecting galaxy clusters at their intersection points. Between those filaments, enormous voids, empty regions like the spaces between threads of a spider's web. This is called the cosmic web, and it is the confirmed large-scale structure of the universe. The web forms through gravity working over billions of years. Tiny fluctuations in the early universe, small variations in density just fractions of a second after the Big Bang, eventually amplified into the massive structures we see today. Matter flows along invisible rivers defined largely by dark matter, gathering at nodes, building filaments, leaving voids behind. The filaments carry galaxy clusters the way rivers carry cities. At their intersections, where matter piles up in the densest nodes, conditions exist that produce some of the most energetic events in the known universe. One of the largest identified filament-scale structures in the observable universe is a complex known as the Pisces-Cetus supercluster complex. It stretches approximately 1 billion light-years across and contains the mass of tens of thousands of galaxies. Our own Laniakea supercluster, itself a structure 500 million light-years wide, sits near its edge. Let that register. We are a small part of a larger supercluster, which is itself a small part of something 1 billion light-years long. The Sloan Great Wall, mapped in 2003, was once called the largest known structure in the universe. It spans roughly 1.37 billion light-years. When it was announced, several cosmologists expressed concern. A structure this size was inconsistent with standard models, which predict that beyond a certain scale, roughly 300 to 400 million light-years, matter should be distributed uniformly. Any coherent structure larger than that should not exist because gravity should not be able to maintain it. The Sloan Great Wall is larger than that. The Pisces-Cetus supercluster complex is larger than that. And there is a structure we will reach later that is larger still. Astronomers debate whether these are true gravitationally bound objects or simply statistical alignments in galaxy distribution. That distinction matters enormously. A gravitationally bound structure means something is actively holding these galaxies together. A statistical alignment means they appear connected from our viewing angle, but have no physical relationship. For some of these structures, the answer remains unclear. That ambiguity is itself significant. What is confirmed is that the universe's matter is not spread evenly. It is threaded through space in a pattern so vast that human civilization has existed for less than a single tick of the clock, required for light to travel its full length. Gravity, working patiently for billions of years, built all of this from nearly nothing. But not everything in the universe works on patient timescales. Some things happen fast, catastrophically fast. And at the center of our own galaxy, something ancient and enormous occasionally wakes from its long sleep. At the center of our galaxy, 4 million stellar masses worth of gravity waits in silence. Most of the time, it is quiet. The black hole at the heart of the Milky Way, known as Sagittarius, a star, is considered relatively dormant compared to the active galactic nuclei found in other galaxies. While quasars and blazars consume vast amounts of material and shine across the observable universe, this one has been described by astronomers as sleeping. But sleeping is not the same as inactive. In 2019, astronomers watching Sagittarius A star with the Keck Observatory in Hawaii witnessed something unexpected. The black hole suddenly brightened by a factor of 75 over a period of just 2 hours. an infrared brightness that far exceeded anything recorded in nearly 20 years of continuous observation. No warning, no obvious cause. A sudden dramatic surge in energy output from the region just outside the event horizon. This event was confirmed through multiple independent telescopes simultaneously. What causes these flares is still under investigation. The leading explanations involve material falling inward toward the event horizon, heating up as it accelerates, and releasing energy as radiation before crossing the point of no return. A star known as S2, part of a cluster of stars orbiting extremely close to Sagittarius A star, passed very near the black hole in 2018. Some researchers believe its passage disturbed surrounding gas clouds, feeding extra material inward and triggering the surge in activity. There is also a gas cloud designated G2 that made a close approach around 2014. Before the encounter, some astronomers predicted a dramatic feeding event, a visible eruption as the cloud was torn apart. The response was less dramatic than anticipated, but not uneventful. The black hole did appear to partially consume material from the cloud. The interaction may still be playing out gradually. And here is where this stops being an abstract story about a distant object. Sagittarius, a star, sits 26,000 light-years from Earth. That is a meaningful distance. But if it were ever to become active in the way other galactic nuclei are, if it were to enter a quasar phase, the energy output directed toward the galactic plane could affect conditions across thousands of light-years in every direction. There is already evidence this has happened. Structures called the Fermi bubbles, confirmed in 2010, are two enormous lobes of high-energy gas and radiation extending above and below the galactic plane. They span roughly 50,000 light-years in total height. They are believed to be remnants of a past active episode, an outburst whose energy carved these structures into the surrounding medium only a few million years ago in cosmic terms. The Fermi bubbles are also interesting because they appear to be sources of high-energy cosmic rays, charged particles accelerated to near the speed of light that constantly rain down on Earth from all directions. Understanding where cosmic rays come from has been a decades-long puzzle. The Fermi bubbles and the processes that created them may be responsible for some fraction of the cosmic rays we detect. The galactic center is not merely the gravitational anchor of the Milky Way, it is an engine that has shaped the entire galaxy's environment across millions of years. Our galaxy carries the signature of its own history, written in gamma rays and carved in energy across a distance that dwarfs every other structure we know locally. 1,000,000 years ago, our most distant ancestors were beginning to walk upright. Above and below the galaxy, the Fermi bubbles were already forming, invisible and vast, pushed outward by the dying energy of a black hole. Feeding event we have no other record of. Our galaxy carries the scars of what its central black hole did in the relatively recent past. The current quiet is real, but it is recent. Sagittarius A star is not dead. It is waiting for the next meal. What comes next on this journey is not a black hole, but a planet, a world where the sky delivers something far stranger than rain. On one side of this planet, it is raining iron, not metaphorically, not poetically. Right now, if you were standing on the night side of the world called WASP 76b, liquid iron droplets would be falling from the sky around you. This was confirmed in a study published in 2020 using a spectrograph instrument mounted on a telescope in Chile. The iron rain was detected through spectroscopic analysis, the technique astronomers use to identify which atoms are present in distant atmospheres, by studying which wavelengths of light they absorb or emit. Here is how the process works. WASP 76b is what astronomers classify as an ultra-hot Jupiter, a gas giant orbiting so close to its host star that a single orbit takes less than 2 Earth days. At that distance, the radiation is so intense that the day side, the face permanently locked toward the star, reaches temperatures around 2,400 degrees Celsius. Hot enough to vaporize iron entirely, turning solid metal into gas. That iron vapor rises into the upper atmosphere, where powerful winds generated by the extreme temperature difference between the two sides sweep it across to the night side. There, temperatures are cooler by nearly 1,000 degrees, still far hotter than any furnace on Earth, but cool enough that iron vapor condenses. It forms droplets. Those droplets fall as iron rain. The boundary between day and night on this planet, called the terminator line, was where the detection was made. Astronomers measured iron atoms arriving at the terminator from the day side, but no iron leaving back toward the day side. The iron disappears there. It falls. No planet in our solar system behaves remotely like this. WASP 76b is tidally locked, meaning the same face always points toward its star, the same way our moon always shows the same face to Earth. One side bakes permanently, the other is in permanent night. The temperature difference between them drives atmospheric circulation so violent that wind speeds are estimated to exceed 18,000 miles per hour. The fastest wind speeds ever recorded on Earth sit below 250 miles per hour. The planet has no surface you could stand on. It is a gas giant, a roiling, superheated atmosphere without a solid foundation. The iron rain falls into deeper atmospheric layers where temperatures rise again. The iron re-evaporates and the cycle repeats. An eternal loop of vaporization and condensation. Iron falling as rain, rising as vapor, crossing the planet in screaming winds, and falling again. What does this mean beyond being an extreme curiosity? It tells us that weather on other worlds operates by rules we had no reason to predict. The same atmospheric physics we know from Earth plays out in configurations our instruments were barely built to detect. The universe is running billions of experiments simultaneously, and some of them produce weather made of metal, and some of them produce worlds made of something even harder. Somewhere in the universe, a world exists where the ground may be made of diamond, not a layer of it, the entire planetary interior. 55 Cancri e is a confirmed exoplanet orbiting a star roughly 41 light-years from Earth. It is classified as a super-Earth, larger than our planet but smaller than a gas giant. It has roughly twice Earth's radius and about 8 times its mass. Based on the composition of its host star and the conditions under which the planet likely formed, scientists have proposed something extraordinary about what lies beneath its surface. The host star of this world has a very high carbon-to-oxygen ratio compared to our Sun. In planetary formation models, when carbon is more abundant relative to oxygen, the minerals that form inside a planet shift dramatically. Instead of the silicate rock that dominates Earth's interior, carbon compounds dominate. Specifically, at the extreme pressures inside a super-Earth, carbon compresses into its densest and hardest known form, diamond. The interior of this planet, under this model, could contain a deep layer of diamond more massive than any deposit ever conceived. The total mass of that hypothetical diamond layer would dwarf every natural resource on Earth combined. The pressure required to sustain it is generated permanently by the weight of the planet itself, pressing inward from all directions. This is a theoretical model, not a confirmed observation. The composition of exoplanet interiors cannot yet be directly measured. The inference comes from stellar composition data and planetary formation physics. It is plausible. It is studied seriously. It has not been proven. The surface of this planet, however, is confirmed to be extreme. It orbits its star at a distance roughly 25 times closer than Mercury orbits ours. A year on this world lasts approximately 18 Earth hours. The surface temperature on the day side exceeds 2,000 degrees Celsius, hot enough to melt rock and keep it liquid. Early observations detected what appeared to be large temperature fluctuations, suggesting volcanic activity on an enormous scale. Rivers of lava possibly flowing continuously across the surface. Later measurements revised some of those initial findings, and the exact nature of the surface is still being studied. Any volcanoes here would not erupt silicate rock the way Earth's volcanoes do. They would erupt carbon compounds, material rich in carbon dioxide, and possibly liquid carbon itself. The atmosphere, if stable enough to persist under that intense stellar radiation, would be thick with carbon gases and clouds. A world where everything from the ground to the sky is dominated by one element: carbon. The same element that forms the backbone of every living thing on Earth. There is something quietly significant about that. The material of life compressed and crystallized into a planetary structure on a world where no life, as we understand it, could survive. The universe takes the same ingredients and builds things unrecognizable. But if a world made of diamond is hard to picture, what comes next has no ground at all. There is a planet with no ground, no bedrock, no continental shelf, no seafloor, nothing to stand on in any direction. A world entirely covered in water so deep and so compressed that the forms it takes have no equivalent anywhere in nature on Earth. GJ1214b is located roughly 42 light-years from Earth and was confirmed by researchers in 2009 using ground-based telescopes. It is classified as a mini-Neptune, smaller than our solar system's ice giants, but significantly larger than Earth. Its diameter is approximately 2.5 times that of our planet. What makes it unusual is its density. Compared to its size, the planet is not very massive. That low density rules out a rocky interior. Combined with its radius and mass measurements, the data points strongly toward an interior dominated by water, but not water in any familiar form. At the pressures deep inside a planet this size, water does not behave normally. Near the surface, if a surface exists, the water would be in a familiar liquid or gaseous state. But as you descend and pressure increases, water molecules are compressed into exotic phases. Researchers call these phases Ice 7, Ice 10, and supersonic water, forms where water molecules are locked into strange lattice structures, or where oxygen atoms form a solid crystal and hydrogen atoms move freely through it like a liquid. These phases have been created briefly in laboratories under extreme experimental conditions. They are real, they exist, but they have never persisted on Earth outside of a small pressure chamber for fractions of a second. On GJ1214b, they make up the bulk of the planet. Going downward on this world, you would pass through a thick, hot, steamy atmosphere, then into a crushing ocean with no visible bottom, then into water phases that become progressively stranger, harder, and less recognizable. Eventually, at the core, temperatures and pressures reach conditions science can model but cannot fully test. There is no continent, no island, no reef, rock, or canyon. The planet is a seamless layered sphere of water in states we cannot hold in our hands. Astronomers have found that GJ1214b's atmosphere is thick and cloudy. The cloud layer blocks attempts to measure atmospheric composition directly. Those clouds themselves may be made of zinc sulfide or potassium chloride particles, exotic chemistry forming at several hundred degrees Celsius. A scorching, cloud-covered, bottomless ocean world. If there is any concept in astronomy that puts the strangeness of other planets in sharp relief, it is this one. We have spent thousands of years mapping every coast and canyon on Earth. Our entire civilization rests on solid ground. Every city, every road, every structure ever built by human hands rests on rock. This planet has none of that. Its entire existence is fluid, pressurized, and layered in ways our architecture, our biology, and our instincts were never designed to comprehend. And what we know about this planet is already more than we know about some anomalies. Because some discoveries challenge not a single world, but the structure of the entire observable universe. The universe should have no preferred direction. That is one of the foundational assumptions of modern cosmology, called the cosmological principle. It holds that on large scales the universe looks the same in every direction and from every location. No center, no edge, no axis, just a smooth, uniform distribution of matter and energy filling space equally in all directions. The axis of evil suggests that may not be true. That name was given by cosmologists not as a political statement, but as an expression of genuine scientific frustration. When the Wilkinson microwave anisotropy probe and later the Planck Space Telescope mapped the cosmic microwave background in precise detail, they found something that had no right to be there. The largest scale temperature fluctuations in the background radiation, the patterns representing the longest wavelengths and broadest features of the early universe, are not randomly oriented. They align. They point in a consistent direction across the sky toward a specific axis that correlates with the plane of our solar system and the direction of the equinoxes. This alignment has been confirmed by two independent missions using different instruments and different analysis methods. A completely random universe should produce these alignments by chance approximately one time in every few thousand trials. The observation is within the realm of statistical possibility, but it is deeply uncomfortable for a model built on the assumption that no direction is special. What could cause it? One possibility is instrumental error or a systematic bias in how the data was processed. Researchers have spent years working to rule this out. They have not been able to do so completely, but many teams believe the signal is real. Another possibility, considered within mainstream cosmology, is that our own local universe creates subtle foreground effects that mimic an alignment. Local matter and motion could introduce small distortions that, when not fully accounted for, produce a spurious axis in the data. A more radical possibility is that the universe genuinely has a preferred direction, that its large-scale structure is not the same in all directions. This would mean that space itself has an orientation, that the Big Bang or the conditions preceding it introduced an asymmetry that persists to this day across the entire observable universe. If that is true, the cosmological principle, the cornerstone of how we model everything, would need fundamental revision. And there is one more possibility that researchers occasionally discuss in the literature. The alignment of this axis with our solar system's orientation could indicate that something about our local position in space distorts what we observe. We may be looking at the universe through a lens we did not know we were wearing. The axis of evil is not a confirmed catastrophe. It is a stubborn anomaly in our best map of the entire cosmos. Confirmed by multiple missions, explained by none, the universe appears to have a direction, and no one knows why. But some objects in this universe are not content to simply exist with unexplained alignment. Some of them erupt violently on a clock. Some black holes do not simply consume, they scream, and they do it on a schedule. Quasi-periodic eruptions are a confirmed astronomical phenomenon, first identified in 2019. They are sudden, intense bursts of X-ray energy originating from the regions just outside the central black holes of certain galaxies. These bursts are not random. They repeat at intervals ranging from roughly 1 hour to several hours, depending on the system. These galactic cores erupt in X-rays, fade back to quiet, then erupt again, like a pulse. The first system confirmed to show this behavior was a galaxy designated GSN 069, located roughly 250 million light-years from Earth. Its central black hole has a mass estimated at around 400,000 times that of our Sun. For months after its discovery, the black hole pulsed in X-rays every 9 hours, each eruption lasting about an hour before fading. Then it went quiet for years. Then it returned. Since that initial detection, roughly half a dozen other systems displaying the same rhythmic behavior have been confirmed. The field is new enough that researchers are still constructing a comprehensive picture of the mechanism behind it. The most widely accepted explanation at this time involves a process called a repeating partial tidal disruption event. In this model, a star gets captured into an orbit that brings it extremely close to the black hole twice per orbit. Each close approach, the black hole's tidal forces strip away a layer of gas and plasma from the star. That material falls inward, heats up to extreme temperatures, and releases the observed X-ray burst. Then the star retreats, the accretion stops, and the system returns to quiet until the next pass. A star being slowly consumed, orbit by orbit, every few hours. Each eruption releases energy equivalent to roughly 1,000 times the total energy output of our Sun, released in under an hour, repeatedly. There is an alternative explanation being explored by separate research groups. In some systems, the quasi-periodic eruptions may be caused not by a star, but by a smaller compact object, possibly a neutron star or low-mass black hole on an extremely tight plunging orbit. Each time this companion passes through the inner accretion disk around the primary black hole, it disturbs the disk and triggers an eruption. Both explanations are considered viable. The truth may differ from system to system. What is clear is that some galactic cores are not simply present and passive. They tick. They erupt on timescales observable within a single human lifetime. An astronomer who discovers one of these systems can watch it pulse, predict the next eruption, and observe it happen. In a field where most processes unfold over millions or billions of years, watching a black hole's feeding behavior repeat on a schedule you can put in a calendar is deeply strange. The universe has rhythms. Some of them are violent, all of them are precise. And some of the most violent rhythms in the universe are responsible for producing every heavy element you have ever touched. Every gold ring, every silver necklace, every platinum dental implant on Earth was forged in a catastrophe that happened before our solar system existed. For decades, scientists understood the origin of lighter elements reasonably well. Hydrogen and helium formed in the Big Bang. Elements up to iron were forged in the nuclear furnaces of massive stars over billions of years. But for the heavier elements, gold, platinum, uranium, iodine, and dozens of others, the origin was a genuine mystery. Stars could not produce them. The temperatures and pressures inside even the most massive stellar cores were not sufficient. The answer required something far more violent. In August of 2017, gravitational wave detectors at the Laser Interferometer, Gravitational Wave Observatory in the United States, and the Virgo detector in Italy simultaneously registered a signal. It was different from the black hole mergers they had previously recorded. It was slower, more drawn out, and it came with something no black hole merger had ever produced: light. Telescopes around the world immediately turned to the source. What they found was a kilonova, the confirmed aftermath of two neutron stars colliding roughly 130 million light-years away. The collision released more energy in a fraction of a second than our Sun will emit over its entire 10 billion-year lifetime. The expanding debris cloud was measured to contain quantities of heavy elements at a scale that answered the long-standing question immediately and definitively. The event had produced an estimated mass of gold and platinum alone, equivalent to roughly 40 to 100 times the mass of Earth. In a single event, every atom heavier than iron in the observable universe traces its origin to moments like this one, confirmed through direct observation in 2017. The process works through a mechanism called rapid neutron capture. In the extreme neutron density of a merging neutron-star pair, atomic nuclei absorb neutrons faster than they can decay, building up the heaviest elements in the periodic table in fractions of a second. These elements are then blasted outward in the explosion, seeding space with material that eventually drifts into nebulae, new star systems, and eventually planets. Our solar system formed from material already enriched by events like this one: the gold in Earth's crust, the iodine in every living cell, the uranium in nuclear reactors. All of it passed through the explosion of colliding neutron stars before it became part of us. The gravitational wave signal from that 2017 collision crossed 130 million light-years to reach Earth. It arrived as a ripple in space-time so small it displaced the detectors by a fraction of the width of a proton. And yet, the instruments caught it. That detection changed our understanding of where we come from. When you hold something made of gold, you are holding debris from one of the most violent events the universe produces. Some things in the universe were born from violence and sent outward with so much energy that the entire galaxy cannot hold them. They are still moving now, and they will never come back. Some stars are fleeing the galaxy. These are real stars confirmed through direct measurement, moving fast enough that the gravitational pull of the entire Milky Way cannot hold them. They will escape. They will cross the outer boundary of our galaxy and enter the intergalactic void, where they will travel alone for billions of years, with no destination and no return. They are called hypervelocity stars, and the fastest confirmed examples are moving at speeds exceeding 3 million miles per hour. The leading explanation for how a star reaches these speeds involves the supermassive black hole at the center of our galaxy. A process described theoretically in 1988 by astronomer Jack Hills and confirmed observationally in 2005 works as follows. A binary star system, two stars orbiting each other, ventures too close to Sagittarius. Star. The black hole's tidal forces disrupt the pair, capturing one star into a tight orbit while slinging the other outward with tremendous velocity. The closer the binary passes to the black hole, the more energy is transferred to the ejected star. This is called the Hills mechanism. It is currently the most accepted explanation for the highest velocity hypervelocity stars. It means Sagittarius A star, even in its current quiet state, has been periodically firing stars out of the galaxy at millions of miles per hour throughout its history. The first confirmed hypervelocity star was discovered in 2005. Dozens more have since been identified. The most extreme cases include stars traveling at speeds that will carry them completely out of the Milky Way within a few 100 million years. Once outside, these stars enter a region containing almost nothing. The nearest major galaxy, Andromeda, sits over 2 million light-years away. Between galaxies, the density of matter drops to nearly zero. A hypervelocity star cast out from our galaxy would travel in darkness and isolation for longer than the current age of the universe, before encountering any other galaxy-scale structure. There is something uniquely isolating about that image. A star born inside the galaxy, perhaps orbited by worlds, torn from a companion by the gravity of a black hole, sent outward at 3 million miles per hour into a void with no destination, traveling further and further from everything it formed alongside for billions of years in a direction that no longer matters because there is nothing in any direction. Some researchers have speculated about whether planets accompanying a hypervelocity star could persist through the ejection. A world orbiting such a star would be carried along into intergalactic space, perpetually lit by its star, perpetually isolated from every other system in existence, with no night sky to speak of, no neighboring stars to observe, no evidence from above that any other structure exists in the universe at all. The study of hypervelocity stars is also yielding hard data about the mass of the Milky Way and the dynamics of the galactic core. Each confirmed trajectory traced backward gives astronomers information about the conditions near Sagittarius A star at the moment of ejection. The galaxy has been losing stars continuously. Some are escaping right now. But there is a boundary beyond which even the concept of escape changes entirely. A distance so vast that the universe itself ensures nothing can ever cross it, regardless of speed. There is a boundary at the edge of everything we can know. No physical wall, no surface or membrane you could orbit or measure directly, but a limit more absolute than any material structure. A point beyond which no light has ever reached us and none ever will. It is called the cosmological horizon, and it is a consequence of something that does not receive nearly enough attention, the expansion of space itself. When people imagine the universe expanding, they often picture galaxies moving through space like objects thrown outward from an explosion. That picture is wrong, and the difference matters enormously. Galaxies are not moving through space. Space itself is stretching. The fabric of space-time is expanding, and galaxies are embedded in that fabric, carried along like raisins in rising dough. This distinction changes everything about how far we can see. The observable universe stretches about 46 billion light-years in every direction. The universe is 13.8 billion years old, but because space has been expanding throughout all that time, the sources of the oldest light we detect are now far further away than 13.8 billion light-years. Beyond the observable horizon, space exists. Matter exists, perhaps galaxies, planets, and structures similar to everything we can observe. There is no confirmed reason to believe the universe ends at our observational limit. It may continue indefinitely. But here is what makes this boundary terrifying rather than simply distant. The expansion of the universe is accelerating, confirmed by observations of distant supernovae in 1998, and now one of the most thoroughly verified findings in all of cosmology. Something called dark energy, which accounts for roughly 68% of the total energy content of the universe, is driving this acceleration. Because of this, there are galaxies we can currently observe that are right now moving away from us faster than the speed of light. Not objects moving through space at impossible speeds, which physics forbids, but space itself expanding fast enough that the distance between us and those galaxies grows by more than 1 light-year per year. Light from those galaxies is still reaching us today because they were closer in the past when that light was emitted. But new light leaving those galaxies right now will never reach us. The space between us and them is growing faster than light can cross it, and the boundary keeps moving outward. Over time, as the expansion accelerates, more and more galaxies will cross our cosmological horizon. Their light will redshift to invisibility. They will disappear from our observable universe permanently. Billions of years from now, astronomers in our galaxy, if any exist, will look out at a sky dramatically emptier than ours. Not because those galaxies were destroyed, but because the universe has carried them beyond the limit of detection. Forever. They will look out and see mostly darkness where we see thousands of galaxy clusters. They may conclude the universe is almost empty. We know better only because we exist at this particular moment in cosmic history, late enough to have mapped it, early enough that we have not yet lost everything to the horizon. The edge of what we can ever know is already moving away from us. And what lies beyond it is, by definition, something we can never confirm. That thought is worth sitting with. The Big Bang did not only create matter and energy, it may have created black holes. Not from dying stars, not from collapsing cores, but from the raw violence of the earliest moments of existence, when the universe was younger than 1 second old, and temperatures exceeded anything that has existed anywhere since. These theoretical objects are called primordial black holes. They have never been confirmed, but they have also never been ruled out. And the implications of their existence reach further than almost any other idea in modern physics. Here is how they would form. In the first fractions of a second after the Big Bang, the universe was not perfectly smooth. Small regions of higher density existed, scattered through the expanding fireball. In most places, these dense patches expanded outward and dispersed. But in some places, the density may have been high enough that a region collapsed inward under its own gravity before it could expand away. A black hole formed from compression, not from a dying star, born in an instant, potentially as small as a single atom containing the mass of a mountain, or far larger. The spectrum of possible primordial black hole masses is vast, from submicroscopic to millions of times the mass of our Sun, depending on the conditions at formation. They would have formed throughout the universe, drifting through space since the earliest moments, interacting gravitationally, but emitting nothing. No light, no radiation, just mass and gravity, silent since before any star existed. And here is where the story becomes personal. Some researchers have proposed that primordial black holes could be a significant component of dark matter, the invisible substance that accounts for roughly 27% of the universe's total mass energy content. Dark matter has been measured gravitationally across the universe for decades, but its identity remains unknown. Primordial black holes match the observational constraints well enough that the idea is considered legitimate and actively tested. If primordial black holes exist in the mass ranges being studied, a population of them could be distributed throughout our galaxy right now. Some potentially within our solar system's gravitational neighborhood, moving silently through space, influencing trajectories in ways too subtle to distinguish easily from other gravitational effects. A hypothesis published in 2016 by researchers at the California Institute of Technology, studying unusual gravitational influences on outer solar system objects, proposed that a large undiscovered body might exist in the outer reaches beyond Neptune. Some physicists have since proposed that this hypothetical object could be a primordial black hole rather than a planet. This idea is speculative. It has not been confirmed, but it has been published in peer-reviewed research and discussed seriously by astronomers and physicists. The methods being used to test it include looking for brief, brightening events caused by a black hole passing in front of a distant star, gravitationally bending and amplifying its light. No detection has been made yet, but the search is ongoing. The possibility that a relic of the Big Bang, a black hole older than every star in the sky, might sit quietly in the outer darkness of our solar system, unseen and unmeasured, is the kind of thought that changes how the word neighborhood feels. The universe may have hidden things inside our own backyard since before Earth existed, and hidden things are a theme that recurs. Because some objects in this universe are not hidden at all. They are visible in the mathematics. They appear in every equation. They simply refuse to be observed. The equations that describe black holes have a mirror image. Every valid solution to Einstein's field equations that produces a black hole also produces its theoretical opposite. A region of space-time from which matter and energy can only exit. Nothing falls in, nothing approaches, everything is expelled outward with no mechanism to reverse the flow. This object is called a white hole. And by the mathematics of general relativity, it is just as valid as the black hole it mirrors. No white hole has ever been observed, not one. In the entire history of modern astronomy, no confirmed detection, no candidate object, no signal consistent with a white hole has been recorded, and yet they cannot simply be dismissed. The reason physicists take white holes seriously, despite zero observational evidence, is that they emerge from the same framework that predicted black holes before they were confirmed, that predicted gravitational waves decades before they were detected, and that has been verified to extraordinary precision across every test ever designed for it. When that framework produces a prediction, ignoring it requires strong justification. A black hole is a region where the escape velocity exceeds the speed of light, meaning everything that enters can never leave. A white hole is the time-reversed version, a region where the approach velocity required to enter exceeds the speed of light, meaning nothing can ever reach it. Matter and energy emerge from it continuously, but nothing can go in. Where would that matter come from? One interpretation connects white holes to black holes through a structure called an Einstein-Rosen bridge, more commonly known as a wormhole. In this framework, matter falling into a black hole might emerge through a white hole at a different location or time in the universe. The two objects would be connected through a tunnel in space-time. This interpretation is mathematically valid. It is almost certainly not physically accessible because the interior geometry of a real black hole is unstable in ways the idealized mathematical solution does not capture. Real wormholes, if they form at all, would almost certainly collapse instantly. But the idea exists within legitimate physics, not science fiction. A second, more recent interpretation comes from loop quantum gravity, an approach to unifying quantum mechanics and general relativity. In this framework, the singularity at the center of a black hole is replaced by a quantum bounce. Matter compressed to extreme density does not reach infinite density. It rebounds. The black hole eventually, over enormous timescales, transforms into a white hole and expels its contents. If this model is correct, white holes exist. They are simply future states of black holes, and the timescales involved are so vast that none have yet reached that stage in the current age of the universe. The gamma-ray bursts detected regularly from deep space are among the most energetic events observed. Some researchers have proposed without consensus that certain unusual bursts might be consistent with white hole activity. These proposals are at the speculative edge of the field. What is not speculative is this: the mathematics of our best confirmed theory of gravity demands these objects exist in some form. The universe does not always ask our permission before behaving as the equations describe. The universe has a size limit for structures. Physics demands it. For a coherent structure to exist, the parts of it must have been in causal contact at some point. In the early universe, information traveled at the speed of light. For two regions of space to have influenced each other enough to form a connected structure, light must have had enough time to travel between them since the Big Bang. That sets an upper boundary. Structures larger than a few 100 million light-years should not exist as connected, gravitationally coherent objects. The universe simply has not been around long enough for them to form. The Hercules Corona Borealis Great Wall is approximately 10 billion light-years across. This object is not 10% larger than the limit. It is not twice the limit. It is roughly 25 times the scale at which structures should be able to exist by any standard cosmological accounting. It was identified in 2013 and 2014 by a team of researchers mapping the distribution of gamma-ray bursts, the most energetic electromagnetic events in the observable universe, across a specific region of sky. Gamma-ray bursts are distributed throughout the universe and on large scales should be distributed roughly uniformly. Instead, a massive excess of them was found clustered in one region, suggesting an enormous concentration of matter, galaxies, and dense structures in that direction. The structure they outlined spans from roughly 7 billion to 10 billion light-years from Earth. It subtends an enormous fraction of the observable sky. If you could see it directly, it would cover a patch of sky roughly 4 times larger than the full moon in one dimension. The scientific response to this discovery was divided. Some researchers argued that the apparent clustering of gamma-ray bursts could be a statistical artifact, a chance alignment that looks like a structure but has no physical coherence. Gamma-ray burst catalogues of that era had known systematic biases, and the sample size was considered by some critics to be too small to draw firm conclusions. Others took the findings seriously and pointed to it as genuine evidence of structure far beyond what standard cosmology permits. As of the current state of the literature, the Hercules Corona Borealis Great Wall remains classified by many researchers as a candidate structure rather than a confirmed one. But candidate structures at 10 billion light-years are not something cosmology can easily dismiss. If real, this object poses a direct challenge to the cosmological principle, the same foundation shaken by the axis of evil. A universe that produces structures 10 billion light-years across is a universe that did not evolve according to the standard model. Something else would need to have organized matter on those scales in the time available. New physics, new forces, conditions before the Big Bang that imprinted structure onto the universe before it began. All of these possibilities are on the table, quietly and seriously, within the cosmological literature. The universe may be organized on scales so vast that our most successful models of it are only locally accurate, like a map of a single city that claims to describe the shape of the planet. 10 billion years ago, some of the most luminous objects in existence were already active. Quasars are the intensely bright cores of distant galaxies powered by supermassive black holes, actively consuming enormous quantities of surrounding material. As gas and matter spiral inward, they heat up to millions of degrees and release energy that outshines every star in their host galaxy, combined sometimes by a factor of 1,000. The most distant quasars we have detected are seen as they existed just a few 100 million years after the Big Bang. The universe was young, barely formed by cosmic standards. Galaxies themselves were still assembling, and yet these quasars were already powered by black holes containing hundreds of millions to billions of times the mass of our Sun. This is the problem. This is what keeps cosmologists awake. Black holes grow by consuming material. The rate at which they can consume is physically limited by something called the Eddington luminosity, the point at which radiation pressure from the energy being released pushes back against infalling material and slows consumption. A black hole growing at the maximum physically allowed rate, called Eddington limited accretion, starting from a stellar remnant of a few tens of solar masses, requires hundreds of millions of years to reach the billion solar mass scale. The universe, at the time these quasars were active, did not have hundreds of millions of years to spare. It had a few 100 million years at most before these objects were already fully formed and shining. Something is wrong with that accounting. Proposed solutions include the possibility that early black holes grew from unusually massive seeds, perhaps direct collapse black holes formed not from stellar death, but from the direct collapse of enormous gas clouds in the early universe. These seeds, if they existed, could have started with tens of thousands of solar masses instead of tens, drastically shortening the time needed to reach observed quasar masses. Another proposal involves periods of super-Eddington accretion, growth faster than the standard physical limit allows. In theory, some models suggest this may be possible under specific conditions that existed in the dense early universe. Neither of these explanations is fully confirmed. Both are active areas of research. What is confirmed is the timeline problem. The black holes existed. Their masses have been measured. The universe was not old enough for them to have grown through standard processes. Something in the early universe was building things faster than the rules should allow. The quasars eventually quieted as their host galaxies consumed the surrounding gas, and the fuel supply shrank. Most are now distant, faded, and visible only because the light took so long to reach us. They are records of a universe that was briefly far more violent and luminous than the one we inhabit. We look at them and see a past that does not match our models of how that past should have gone. And not everything that broke the rules became a quasar. Some things simply went dark and kept moving. There are planets drifting through the galaxy right now with no star, no warmth from above, no light, no orbital path connecting them to anything. Just rock or ice or whatever they are made of, moving through the interstellar dark in complete isolation at temperatures approaching absolute zero. These are called rogue planets or free-floating planets, and they are confirmed to exist. Gravitational micro-lensing surveys have detected dozens of candidates, and statistical analyses of those surveys suggest they may be extraordinarily common. Some estimates based on survey data published around 2021 suggest there could be billions of rogue planets in the Milky Way alone, possibly more rogue planets than stars. They form in several ways. Some are ejected from planetary systems during the chaotic early period of orbital formation, when gravitational interactions between young planets can send one member of the system on an escape trajectory. Computer simulations of solar system formation consistently produce ejections, and our own solar system may have ejected one or more planets in its early history. Others may form directly in interstellar space from collapsing clouds of gas and dust, following a formation process similar to star formation, but involving too little mass to ignite nuclear fusion. These objects sit in a category between planet and failed star. The surface of a rogue planet is cold beyond easy description. Without stellar radiation, surface temperatures fall toward the ambient temperature of deep space, just a few degrees above absolute zero. Any atmosphere would freeze and fall as snow. Any liquid water would have solidified billions of years ago. The planet moves through complete darkness, lit only by the dim background of distant galaxies, which would provide no meaningful warmth. But here is the detail that complicates the simple picture of dead, frozen worlds. Some rogue planets may retain geothermal heat from their interiors for billions of years. Rocky planets large enough to maintain radioactive decay in their cores generate internal heat, regardless of external conditions. And some rogue planets, particularly those in the mass range between Earth and Neptune, may retain thick hydrogen atmospheres that act as insulators, trapping internal heat and potentially maintaining liquid water somewhere beneath the surface, even in the absence of any star. This idea was published in research papers and has been discussed in the context of possible habitability. A subsurface ocean heated from below, shielded from the absolute cold above by an insulating atmosphere and kilometers of ice, might exist in the interior of a rogue planet drifting through the galaxy's void. Life without a star. Chemistry without light. Biology powered entirely by the slow decay of radioactive elements in a hidden ocean, circling nothing, going nowhere, in a darkness so complete that no observation from the outside would betray its presence. That possibility has not been confirmed. It has not been ruled out. The rogue planet keeps moving, silent, dark. Perhaps not entirely dead, but even a rogue planet will eventually face what everything in this universe cannot avoid. Everything in the universe will be destroyed, not collapsed, not frozen, not faded. Destroyed at the atomic level. Every galaxy, every star, every planet, every molecule, every atom, every subatomic particle will be pulled apart by the same force currently accelerating the expansion of the universe. This is the Big Rip, and it is a theoretically sound endpoint that follows directly from what we have already confirmed about dark energy. Dark energy is real. Its accelerating effect on cosmic expansion has been confirmed through multiple independent methods. The uncertainty is not whether it exists, but what it is, and whether its strength remains constant over time. If dark energy is a fixed property of space, called a cosmological constant, the universe expands forever, but the rate of acceleration stays steady. Galaxies eventually drift beyond the cosmological horizon. Stars burn out. Black holes slowly evaporate through Hawking radiation over timescales beyond imagination. The universe reaches a cold, dark, motionless equilibrium called heat death. Everything ends, but gradually. If dark energy grows stronger over time, the outcome is different and much faster. In the Big Rip scenario, the strength of dark energy increases as the universe expands. At first, the effect is imperceptible. Galaxies separate. Then, closer to the end, the expansion tears apart gravitationally bound structures. Galaxy clusters disperse. Individual galaxies are pulled apart. Then solar systems. As the expansion overwhelms the gravitational binding between stars and their planets, the final moments accelerate dramatically. Roughly 30 minutes before the end, planets are torn from their stars. Approximately 16 minutes before the end, individual planets are ripped apart, their rocky surfaces and iron cores unable to hold together against the expansion. In the final moments, stars are destroyed, then atoms, then subatomic particles. The expansion of space, the same gentle stretching that carried galaxies apart over billions of years, reaches down to the smallest scales and dismantles everything. This end depends on the nature of dark energy, specifically whether the parameter describing its behavior, called W, sits at a value of -1 or becomes more extreme over time. Current measurements place W very close to -1, consistent with a cosmological constant. But the measurement uncertainties are large enough that a slowly increasing dark energy cannot yet be ruled out. Whether the Big Rip happens or not is a question the universe has not yet answered. The data does not currently favor it, but it does not exclude it. Researchers studying dark energy are in a very literal sense trying to determine the final fate of everything that exists. The universe began in an instant. It has run for nearly 14 billion years. And one of the honest, unresolved questions in cosmology is whether it ends in a slow fade or in a final, total unraveling that reaches into the interior of every atom and tears it open. Nothing would be left, not even the ingredients to begin again. But while that ending remains distant and uncertain, there are places in this universe right now that feel like previews of alien extremes. Places that exist in our own solar system, close enough to visit, strange enough to defy every intuition we carry. One of the strangest oceans in the solar system is not made of water. Titan, the largest moon of Saturn, is the only body in the solar system other than Earth confirmed to have stable liquid on its surface. Rivers flow there. Lakes fill low-lying basins. Seas stretch for hundreds of miles. Rain falls from clouds and feeds those bodies of liquid through drainage systems. But none of it is water. Titan's surface sits at around -179 degrees Celsius. At that temperature, water is frozen as hard as granite. The liquid filling Titan's lakes and seas is methane, along with ethane and other hydrocarbons. Organic molecules that on Earth are the building blocks of fuels and plastics. The largest confirmed sea on Titan, called Kraken Mare, covers roughly the same area as the Caspian Sea on Earth. It is filled with liquid methane cold enough that oxygen gas, if released there, would instantly freeze and fall as frost. The shoreline is carved not by wave erosion, but by methane tides driven by Saturn's gravity. The seafloor is likely coated in organic sediment, complex carbon chemistry that has been accumulating for billions of years. Titan's atmosphere is thick, nitrogen-dominated, and laced with organic chemistry. Ultraviolet light from our sun breaks methane molecules apart in the upper atmosphere, and the resulting chemistry produces a haze of complex organic compounds called tholins. These tholins drift down and accumulate on the surface and potentially dissolve into the hydrocarbon seas. On early Earth, before life began, something similar may have happened. Organic chemistry building up in liquid environments, simple molecules reacting, combining, forming more complex structures over millions of years. The path from chemistry to biology on Earth is still not fully understood, but liquid environments filled with organic molecules appear to be a key ingredient. Titan offers a frozen, extreme version of that same scenario. Whether chemistry in liquid methane can produce anything resembling biological processes is genuinely unknown. The energetics are different from water-based chemistry. Methane is a poor solvent compared to water for many biological reactions. But the universe has demonstrated repeatedly that wherever chemistry can run through repeated cycles in a liquid medium, complexity tends to emerge. In 2027, NASA's Dragonfly mission is scheduled to arrive at Titan. A nuclear-powered rotorcraft will fly through the thick atmosphere, landing at multiple sites across the surface, directly sampling the chemistry of this hydrocarbon world for the first time. It will be the first time humanity has placed an instrument into the liquid-adjacent environment of another world sea and asked the question directly. Is there chemistry here that we have not seen before? The answer is almost certainly yes. Whether it has crossed the threshold into something more is one of the most important open questions in science. And if Titan feels like a cold, dark, quiet kind of strange, the next destination operates by completely opposite extremes. Venus should be Earth's twin. It is almost identical in size, similar in mass, and sits at a distance from our star that by rough calculation should allow for temperate conditions. Instead, its surface is hotter than some stellar interiors. The confirmed surface temperature on Venus is approximately 465 degrees Celsius. That is hotter than Mercury, Despite Mercury being far closer to our star, it is hot enough to melt lead. It is hotter than the temperature required to fire pottery in a kiln. It maintains this temperature constantly, day and night, pole to equator. Because of a runaway greenhouse effect so extreme, it has become the textbook definition of the term. Venus's atmosphere is roughly 96% carbon dioxide. The atmosphere is also incredibly dense. Standing on the surface, you would feel atmospheric pressure roughly 92 times greater than what you feel at sea level on Earth. That is equivalent to the pressure you would experience about 900 meters underwater in Earth's oceans. The combination of heat and pressure creates conditions where no spacecraft has ever survived more than about 2 hours. The Soviet Venera landers sent between 1970 and 1982 are the only craft ever to return images from the surface. Each one was slowly destroyed by the heat and pressure within minutes to hours of landing. The images they transmitted showed a landscape of flat rock slabs under an orange-lit sky before the transmission stopped permanently. The sky above Venus's surface glows orange because the thick clouds above are made of sulfuric acid. These clouds reflect most sunlight and generate acid rain that never reaches the surface, evaporating in the intense heat before it arrives. But within those clouds, at an altitude of roughly 50 kilometers, conditions change completely. At that height, pressure and temperature on Venus fall to ranges broadly comparable to Earth's surface. Approximately 1 atmosphere of pressure. Temperatures around 30 degrees Celsius. This atmospheric layer receives sunlight. It contains water vapor in trace amounts. It has the chemical ingredients for certain kinds of chemistry. In 2020, a research team published a paper claiming detection of phosphine gas in Venus's atmosphere at that altitude. Phosphine on Earth is produced almost exclusively by biological processes or industrial chemistry. The claim generated enormous attention and immediate scrutiny. Subsequent analyses raised questions about the data processing, and the detection was significantly revised downward. The status of phosphine on Venus remains unresolved and debated, but the question it raised did not disappear. The cloud layer of Venus at 50 kilometers altitude is one of the few places in the solar system where the physical conditions are not immediately lethal to Earth-based biology. A surface that destroys spacecraft in minutes. A cloud layer where life might theoretically float. Venus is a world of extremes stacked directly on top of each other, divided by altitude. And both extremes are operating on a scale that makes the next destination feel almost invisible, because some of the most significant things in the universe cannot be seen at all. Most of the universe is invisible. Not dark in the way space between stars is dark, not transparent like glass, where you could in principle see through it with the right instrument. Genuinely invisible. It does not emit light, it does not absorb light, it does not interact with the electromagnetic force at all. It passes through ordinary matter, as though ordinary matter is not there. Dark matter accounts for roughly 27% of the total mass energy content of the universe. This is not a rough estimate. It is one of the most thoroughly cross-verified numbers in modern cosmology, confirmed through galaxy rotation curves, gravitational lensing, large-scale structure formation, and the cosmic microwave background. The existence of dark matter is not seriously debated. What it is, however, remains completely unknown. The galaxy we live in is embedded inside a dark matter halo, a roughly spherical distribution of this invisible material extending hundreds of thousands of light years beyond the visible disk of stars and gas. Every galaxy in the observable universe has one. The dark matter halos were there first. their gravity providing the scaffolding along which ordinary matter collapsed to form the galaxies we see. Within our own galaxy, dark matter is not distributed smoothly. Simulations of structure formation consistently predict that galactic halos contain smaller substructures, clumps of dark matter called subhalos or dark matter mini-halos distributed throughout the galaxy, including in the region our solar system occupies. These clumps would be detectable only gravitationally. If the solar system passed through or near a dark matter subhalo, the gravitational influence could, in principle, produce measurable perturbations in the orbits of distant solar system objects over long timescales. Detecting these effects requires either extremely precise measurements over very long baselines or a close enough encounter that the perturbation exceeds current measurement thresholds. No confirmed detection of a dark matter clump through local gravitational effects has been made. The leading candidates for what dark matter actually is include weakly interacting massive particles, which have been searched for in underground detectors for decades without confirmed detection. Axions, extremely light particles predicted by certain extensions of the standard model of particle physics, are another strong candidate and are being actively searched for in new experiments. Primordial black holes, as discussed earlier, remain a possibility in certain mass ranges. Every proposed candidate has survived some tests and failed or been constrained by others. None has been confirmed. The universe is mostly made of something we cannot see, cannot touch, cannot detect directly, and cannot name with certainty. We know it is there because of what it does to the things we can see. Gravity is the only language dark matter speaks to us in, and we are still learning to read it. What sits even further from confirmation, but even closer to the edge of what physics allows, is a category of matter stranger than dark matter, stranger than neutron matter, stranger than anything ever placed in a particle accelerator. Matter, as we understand it, is made of atoms. Atoms are made of protons and neutrons. Protons and neutrons are made of quarks, specifically two types, up quarks and down quarks, bound together by the strong nuclear force. Under normal conditions, quarks cannot exist individually. They are permanently confined inside particles. The strong force holding them together actually grows stronger as you try to pull them apart, making isolation impossible under any conditions found on Earth. But at extreme pressures, the situation may change entirely. At densities far beyond anything achievable in a laboratory, the energy required to maintain individual proton and neutron boundaries may exceed the energy of simply allowing quarks to exist in a free, shared state throughout the entire object. This phase of matter, where individual quarks roam freely rather than being bound in particles, is called quark-gluon plasma, and has been briefly created in heavy ion collisions at particle accelerators for fractions of a second. At the pressures inside the most extreme neutron stars, a permanent version of this state may form in the core. And if conditions are right, the pressure could convert some of the up and down quarks into a third type, strange quarks. The resulting material, called strange quark matter, is hypothesized to be extraordinarily stable. More stable, potentially, than ordinary nuclear matter. If a neutron star's core reaches the pressure required to form it, the conversion might propagate outward, transforming the entire star into a strange quark star over time. A strange quark star would be smaller and denser than a neutron star of the same mass. Its surface would be a direct boundary between strange quark matter and the vacuum of space, with no normal nuclear matter in between. The surface would be extraordinarily sharp within a few atoms' thickness, below which matter exists in a state that no laboratory has sustained for more than a fraction of a microsecond. The object catalogued as RXJ 1856.5-3754, visited earlier in this journey, remains one of the candidate strange quark stars based on its anomalously small radius. The pulsar designated PSRJ 095-2-0607, with its mass exceeding standard neutron star predictions, is another. Both remain officially unconfirmed as strange quark stars. The reason confirmation is so difficult is that the observable signatures of a strange quark star differ from those of a neutron star in subtle ways that require either extremely precise radius mass measurements or detection of specific emission signatures not yet fully characterized. What strange quark matter means conceptually is that the universe may contain objects made of a phase of matter that has never existed on Earth, that cannot be created in any facility currently in operation, and that if a small fragment ever came into contact with ordinary matter, some models predict it would convert that matter into strange quark matter as well, propagating through any normal matter object it touched. This is called the strange nugget hypothesis. It is speculative. The conditions under which such a fragment could escape a quark star, survive in space and interact with other matter are not well defined. But the universe is not required to ask for permission before running experiments at scales we cannot replicate. Something even less subtle erupted from the center of our galaxy not long ago, and the scars are still there. In 2010, astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope found something in the data that no one had expected and no model had predicted. Erupting above and below the plane of our galaxy, centered precisely on the galactic core, were two enormous lobes of high-energy gas and gamma radiation. Each one extended roughly 25,000 light-years from the galactic plane. Together, they form a structure about 50,000 light-years tall, spanning nearly half the width of our galaxy. They had been hiding in plain sight because they are visible only in gamma rays and microwave wavelengths, the forms of light the human eye cannot detect, and that require space-based instruments with specific calibration to isolate from background noise. They are called the Fermi bubbles. Their edges are surprisingly sharp, a feature that indicates the boundary between the lobe material and surrounding gas is well defined and relatively young. If these structures had been slowly inflating over billions of years, their edges would have diffused and blurred. Instead, they look freshly carved. The leading explanation is that they are remnants of a past active period of Sagittarius A star, our galaxy's central black hole. At some point in the relatively recent past by cosmic standards, somewhere between 1 million and a few million years ago, the black hole entered a more energetic phase. It consumed large quantities of material and generated jets or wide-angle winds of energy powerful enough to drive gas upward and downward out of the galactic plane at high velocity, inflating these two lobes over hundreds of thousands of years. If this explanation is correct, the Milky Way had an active galactic nucleus not long ago in cosmic terms. It was not a quasar-level event, but it was significant enough to leave structures visible across an area larger than half the galaxy. 1 million years ago, our most distant ancestors were beginning to walk upright. Above and below the galaxy, the Fermi bubbles were already forming, invisible and vast, pushed outward by the dying energy of a black hole. Feeding event we have no other record of. The Fermi bubbles are also interesting because they appear to be sources of high-energy cosmic rays. Charged particles accelerated to near the speed of light that constantly rain down on Earth from all directions. Understanding where cosmic rays come from has been a decades-long puzzle. The Fermi bubbles and the processes that created them may be responsible for some fraction of the cosmic rays we detect. The galactic center is not merely the gravitational anchor of the Milky Way. It is an engine that has shaped the entire galaxy's environment across millions of years. The Fermi bubbles are the most visible evidence of that. Our galaxy carries the signature of its own history, written in gamma rays and carved in energy across a distance that dwarfs every other structure we know locally. And if one galaxy can carry structures this strange on scales this large, it raises the question of what happens when entire groups of galaxies arrange themselves in ways that no force we have fully described seems able to explain. Galaxies should not agree with each other about which way to spin. Angular momentum in the early universe was distributed essentially randomly as matter collapsed to form galaxies across billions of years. The direction of rotation each galaxy developed should have been independent from its neighbors. There is no known mechanism in standard cosmology that would cause galaxies separated by millions of light years to share a preferred orientation. And yet, several studies have found exactly that. A series of surveys mapping the orientations of galaxy spin axes in large-scale structures have found statistically significant alignments in several regions of the sky. In one well-documented case involving a supercluster-scale filament, a research team found that spiral galaxies along the filament showed spin-axis orientations that aligned with the filament direction far more often than random chance would predict. These alignments are statistical signals sitting at roughly 3 to 4 standard deviations above random expectation. In the strongest cases, significant enough to be taken seriously by the community, but not at the level of certainty that ends debate. The most striking findings have involved quasars. In 2014, a study of over 19,000 quasars found that in the largest cosmic structures, quasar spin axes tended to align with each other, and with the large-scale structure of their environment across distances of 1 billion light-years. Two objects separated by 1 billion light-years, showing correlated orientations. No causal mechanism could connect them at that distance. No force, no signal, no interaction could have traveled between them in the time available since the Big Bang. The researchers who reported these alignments proposed that the correlations reflect conditions in the primordial universe, patterns established before or during the earliest moments of expansion that imprinted preferred directions into the distribution of angular momentum across the cosmos. If true, the rotation of galaxies we observe today carries a memory of conditions that existed in the universe before any structure formed. The spin of a galaxy 1 billion light-years away and the spin of a galaxy 1 billion light-years in the opposite direction may both be responses to the same primordial signal, written into the universe before either of them existed. That idea connects naturally to the axis of evil, to the cold spot, to every anomaly encountered on this journey that suggested the universe has large-scale patterns not predicted by standard models. A recurring theme emerges. The universe at the larger scales may be more structured, more directional, more patterned than our most successful theories predict. These anomalies span observations as different as temperature maps of ancient radiation, the orientation of active galactic nuclei, the distribution of gamma-ray bursts, and the spin of spiral galaxies. They may each have independent explanations, or they may be facets of a single underlying reality we have not yet described. The most unsettling thing about the universe is not any one of these findings. It is the possibility that they are connected. And if they are, the connection was established at a moment we are about to face directly. Everything ends here, not with fire, not with collision, not with any force violent enough to register as an event. The universe ends in the quietest, most absolute way imaginable. It reaches equilibrium, and equilibrium at cosmic scales is indistinguishable from nothing. The second law of thermodynamics states that entropy, The measure of disorder in a closed system always increases over time. Energy spreads. Concentrated forms of energy, stars burning, black holes feeding, particles colliding, always move toward more distributed, less usable forms. The universe, as a closed system, is always moving toward its maximum entropy state. That state is called heat death, and it is the confirmed long-term trajectory of the universe under current physics. It does not happen quickly. The current age of the universe is roughly 14 billion years. The last star capable of hydrogen fusion will burn out in approximately 100 trillion years. A number so large that 14 billion years, the entire history of everything, represents barely 1/10,000th of the time remaining before stellar death. After that, the universe enters the degenerate era. Brown dwarfs and white dwarfs persist, cooling slowly for quadrillions of years. Stellar remnants and dead planets continue orbiting, their paths decaying imperceptibly through gravitational radiation. Then, the black hole era. All other matter eventually falls into the black holes that remain or escapes into the void. Black holes themselves slowly evaporate through a quantum process called Hawking radiation. A black hole the mass of our Sun takes longer than 10 to the 67th years to evaporate completely. Ton 618 at 66 billion stellar masses would persist for timescales that make even that number look brief. But they all evaporate eventually. This is a confirmed theoretical prediction that has never been directly observed, because no black hole is old enough. But the physics is considered robust. The final particles emitted by the last evaporating black hole drift outward into a universe containing nothing else. No structure, no temperature gradient, no concentration of energy that differs from any other. No place where any event can occur because events require energy differentials, and energy differentials no longer exist. The universe arrives at perfect, total, eternal stillness. Not empty in the way space is empty now, where particles and radiation still fill every region. Empty in a deeper sense. Every quantum of energy spread as uniformly as physical law allows. With no further evolution possible, no clock ticks, no atom vibrates above its ground state. No signal travels, because no signal carries energy that differs from its surroundings. Time becomes meaningless because nothing changes. This is where the laws of physics lead, followed to their end. The same universe that produced the Bootes void and the Great Attractor, that built Ton 618 and forged gold in neutron star collisions, that launched hypervelocity stars into the intergalactic void and grew structures 10 billion light-years across, will arrive at a silence so complete that no evidence of any of it will remain. Every object visited on this journey will be gone. Every anomaly, every terrifying place, every structure that defied our models, dissolved into uniformity. The universe keeps every secret. Eventually, we are here, in the brief interval between the beginning and the stillness, in the window where stars burn and structures exist, and something looks up and asks where all of this came from. That question may be the most remarkable thing the universe has ever produced, and it is still waiting for an answer.